So thank you, San, for that very generous introduction. So today I'm, very happy for this opportunity to talk to you about a work of ours called Deep Shape Models for 3D Medical Image Delineation. And the general idea of this work is to impose a shape prior for medical image segmentation. So let's first just get some acknowledgements out of the way. So first off, this work was done while I was an employee at MICCAI. I was very happy for the opportunity. The work was primarily performed by an intern under my supervision named Ashwin. So I want to acknowledge his contributions. And we were very, very happy that it was published at AAAI 2022 and actually was given an oral presentation. So we were very, very pleased with that recognition. So I'm going to break down the talk into three main sections. First, I'm going to try to motivate why you want to add anatomical priors to segmentation and some of the history. Then I want to talk about how shape constraints are used and incorporated within deep learning, if at all. And then finally, I think these two sections will motivate enough of our work, which, as I mentioned, was deep implicit models for 3D medical image delineation. So let's try to talk about the history and motivation. So why add a shape prior? So I don't think I need to convince anyone here that segmentation delineation is a critical aspect of medical imaging analysis. And now when we look at human anatomy and a lot of anatomical structures, we can notice that they follow a constrained distribution of shapes. What I mean by that is, we can look at a shape and immediately tell, okay, that's a liver, or that doesn't look like a liver, there's something wrong with that. So that tells us that there's kind of like a low dimensional, subspace that these shapes live on, despite being very highly complex objects in their native space. This distribution can be statistically described, and this anatomical constraints could serve and arguably should serve as a strong prior to parameterize or constrain segmentation. Now, prior to deep learning, this concept actually, or this philosophy is actually really predominant. In particular, there were techniques called statistical shape models. There are many other techniques, but statistical shape models were one of the workhorses prior to deep learning. And statistical shape models, the way that they work is that they break down the segmentation process into three main steps. First is they construct an anatomical statistical shape model. So they try to statistically describe the way shapes vary. Then they want to use that model. And the way they use that is they want to fit that model to a new image. And then finally, there will be some details that may not be captured by the statistical shape model. So they may perform some local fine scale surface refinements to kind of correct that. So it's kind of like the three core components of classic statistical shape models. So let's go into each in a bit of detail. So the first core part is actually constructing that shape model. So historically, statistical shape models use something called point distribution models. There were other approaches used, but PDMs were, by far the most dominant approach. And so the way that PDMs work is that you collect a set of K landmarks for each shape. So here, for visual clarity, I'm showing a non-medical example. I'm showing a human face. But what you would do for each shape is you'd collect, like say, a landmark, the tip of the nose. That might be one landmark for every shape. Now, each landmark is associated with three coordinates, X, Y, Z coordinates. And so you take all K of those and flatten them into a 3 times K vector. Now what you do is you now have a collection of vectors for every shape, and you actually can conduct statistics on those vectors. So for example, you can calculate the mean shape by taking a mean vector, and that actually will often give you quite a meaningful shape. You can conduct PCA analysis on the point distribution model, and the modes of variation that come across there can be quite semantically meaningful. They can describe major, what we would consider the major modes of variation, and that's what's being shown here, where we're varying the first, the second, and the third mode of variation for the PCA. And so you can oftentimes, project this very high dimensional 3 times K vector into a much, much smaller subspace which reflects, again, the fact that these shapes live on a lower dimension subspace. So once you construct a shape model, you want to do something with it. In our case, what we want to do is we want to use it to segment an image in a constrained way. So once you have a shape model, segmentation is now reduced to finding rigid pose. So basically, you want to find the translation scale and rotation of your model and non-rigid pose. So typically, that means the PCA loadings that will deform your shape. And so you want to find these kind of global parameters to fit the image in question. Again, we're showing a computer vision example on the left just for clarity. So prior to deep learning, there are often different types of classifier techniques that were used, or like a random forest or probabilistic boosting tree. Handcrafted features were often used, like Haar wavelets. And the problem, though, was still very difficult because it's a very large search space, because you have to search the best combination of like the 9 rigid pose parameters and however many PCA loadings you have. So you have to come up with other techniques to kind of reduce that search space, like marginal space learning and active shape models. Finally, the third step that you would often see in statistical shape models is you have some local deformations. So you're not going to capture everything, all manners of how shapes can vary. So you often need to have some local deformations just to capture those fine scale details. And there's different ways to do that. You do mesh-based, mask-based, level set-based. So there's a lot of techniques on how to do that. So given that state, what were some of the challenges and limitations of these approaches? So what we want to focus on here, one of the major disadvantages is that the point distribution model requires that you capture a set of landmarks for each shape. Now, if that means that you want to, densely represent how a shape varies, that means you have to have a set of dense landmarks. Now, for the human face, that may work. You may be able to have semantically meaningful landmarks across my face and someone else's face that mean the same thing. But how do you really do that for something like the liver? How do you have a set of dense landmarks for the liver? For example, this point here, what's the best corresponding point on another liver? It's not obvious. In fact, it's actually, it's an underdetermined and unsolved problem. And so a lot of the research and focus on statistical shape models, there was a lot of work just on capturing point correspondences when they weren't indeed obvious. And so this, I would say, is a kind of a major challenge and limitation of these kind of classic point distribution models. Okay, so what I tried to give you here was sort of a short survey of how anatomical constraints were incorporated prior to deep learning. And so let's just talk about what's being done in the deep learning era. So first of all, we obviously have to talk about fully convolutional networks. I don't think it's an exaggeration to say that when we think about deep learning segmentation, we basically think about fully convolutional networks. These approaches are essentially the backbone for almost all leading approaches today. And the way FCNs work is that they use a purely bottom-up pixel or voxel-wise segmentation. So they segment voxel by voxel based on just the context and the neighborhood that it sees. FCNs, obviously, they are the backbone in terms of all the winners of leaderboards and challenges today, and they essentially dominate segmentation. So you might ask, like, what is the problem? So I would say that there's actually two main, limitations with FCNs, despite their definite strengths. The first problem, I think, is the bigger problem, and that's on the left, is that their bottom-up approach means that they're completely unconstrained. And an issue with that is that they can catastrophically fail on new data because there's no guarantee that they're going to provide a segmentation that sort of makes sense. And what I mean by that is sometimes they can make an error that would be really, really obvious to a human, for example. A human wouldn't make that error. Like, for example, here, we have the winner of the LITS challenge on the left. And on the LITS data, it does quite well. But if we present it with new data, this is clinical data, so it has some features it hasn't seen before, new lesion types or treated lesions or new comorbidities. It can make really egregious errors. Like, for example, here it's leaked into the spleen, and no human would make that error because it's obviously not a liver shape. Liver doesn't follow that shape. And in fact, no classic statistical shape model would make that error either. It's also has this huge hole in here because it hasn't seen a treated lesion before, and so it doesn't know what to do. And so while classic statistical shape models may lose to FCNs and challenges, we did lose something in terms of that kind of guarantee on, maybe not strict guarantees, but on the confidence in terms of its behavior and robustness. The second issue is FCNs, they typically work on a mask basis. So they output, they're given an input, image input, and they output a mask. So voxel by voxel discretization. There's typically large interslice thickness there. So the masks that can result if you want to render the surfaces can be quite ugly. You have these stairwise effects. Typically, actually, what we want is we want a high quality surface as the end result. Now, you can sort of address this with some pre-processing or post-processing, but we did kind of lose this ability to natively produce high quality surfaces when we moved from classic SSMs and other approaches to FCNs. Okay, so the importance of incorporating anatomical constraints has been recognized by others in the deep learning era. So there has been some work. Now, I'm not going to pretend that this is an exhaustive list. I'll just try to give like an idea of what's been done. There has been some work that have incorporated kind of classic point distribution models within CNNs, but these, not only do they suffer from the issues with point distribution models where you have to kind of come up with a contrived set of landmarks for each shape, they often don't incorporate rigid pose. So it means that they have to be used in a very constrained setup. And so they're not, I would argue they're not really a true statistical shape model in that sense. Now, another approach is kind of what we call implicit anatomical priors. And I think this is the most successful way in the deep learning era to incorporate some anatomical constraints. And the way that these approaches work is, I think the adversarial one is the easiest one to understand, is that you take a typical FCN, and then at the end of it, you stick on a discriminator that is trying to discriminate the mask output of the FCN versus ground truth masks. And so essentially the discriminator is trying to learn the distribution of what makes a good looking mask versus a bad mask. And the CNN is trying to learn how to fool that discriminator. So you now have some implicit anatomical constraints in there. I think this is a very effective and straightforward way to go to add some robustness. There is some limitations with it. The one issue is that it's an implicit constraint. So we can't really interpret what sort of constraints it's learning. It's hard to predict or understand what it will do. It's very data driven. So we may not, we may not be able to place a ton of confidence in what it'll do given a new situation. And the other issue is that it also encodes rigid pose as part of this constraint that it's this implicit constraint that it's learning. So it's a shape, the same shape, but translated a little bit. We could have a different implicit representation in there. So despite their, I do advocate for this approach, but they do have some limitations. I won't go into this, but there are some other ways to incorporate anatomical constraints beyond the two examples that I mentioned. Okay, so like I said, I didn't give an exhaustive outline, but I think I can confidently say that the deep statistical shape models are quite rare. And when they are implemented, they still rely on point distribution models, which does require those correspondences I mentioned. Current deep statistical shape models do not fit rigid and non-rigid poses. There are implicit anatomical constraints that I mentioned, which do seem to improve things, but they're not really a true statistical shape model. And I think it's fair to say there's no true deep statistical shape model that can rival today's state-of-the-art FCNs. Okay, so I've tried to essentially, discuss, I've given a survey of how people incorporated anatomical constraints prior to deep learning, some efforts in deep learning. And now I think we've, given enough a survey to hopefully motivate our work, which is called Deep Implicit Models for 3D Medical Image Delineation. And this is by no means the be all and end all of segmentation. I think It's kind of the first, our first foray into marrying statistical shape models with deep learning. And we hope that it will spur kind of further research and more people to look at this general, this kind of philosophy and general idea to incorporate anatomical constraints in a way that adds robustness, not necessarily implemented in the same way that we did, although we think we have a good implementation. So this is our approach. So like classic statistical shape models, deep implicit statistical shape models are broken down into 3 core components. The first core component is you have to construct a statistical shape model of shape variation. The second core component is pose estimation. So we want to do something with that shape model. In this case, use it to segment an image. The third core component is then a local fine scale refinement to capture details not captured by our shape model. So we'll go into each component in turn to hopefully explain how it works. So the first part of our approach is constructing a shape model. Now, our approach uses the concepts of deep implicit shapes. So deep implicit shapes, and particularly we build off of a work called Deep SDF. So Deep SDF and 2 concurrent works that are published very close together really kicked off this whole field of implicit shape models. It's a very exciting field. They've seen a lot of success in computer vision, and now I see that it's becoming more and more popular in medical imaging. In the latest MICCAI, I was fortunate enough to be an area chair, and I noticed that actually there was more and more works that were incorporating implicit shapes in some way. So that's the same concept that we build off our model off of. And so before getting into a statistical shape model, let's just make sure we understand how you would model one shape implicitly. So let's say you have one shape you want to model. It can be a mask or a mesh or whatever, but let's turn that into a signed distance function. What that means is that if we turn it to a signed distance function, it means that for any point, any 3D coordinate, we can get the signed distance to the boundary. Typically, we do positive outside and negative inside. That's just a convention. So once we construct our signed distance function, we can then sample a very large number of SDF values and XYZ coordinates. So, maybe we sample 500,000 of them. So we have 500,000 3D coordinates and corresponding SDF values. Then we'll train a multilayer perceptron. So that's just a fully connected network that takes the 3D coordinates as input. And it's tasked, it's trained to essentially regress the corresponding SDF values. So the SDF values are the labels. So assuming that you have this MLP well-trained, what ends up happening is that the shape is now implicitly represented by the network weights. So even though it's implicitly represented by the network weights, that you can still render the shape and actually view it and look at it. And the way that you would do that is you would, for example, take a uniform grid of XYZ values, put them in one by one into your MLP, collect the SDF values, and organize that into a volume, which you can then render. You can convert that to a mesh. You can do whatever you want to it. Now, the nice thing about this is once you have your MLP trained, is that MLP produces smoothly varying SDF at any resolution. So essentially, I can smoothly vary the XYZ values, and I get a smoothly varying SDF. So I get a really, really high quality surface. So that's how you represent one shape implicitly. So now what would we do if we want to represent a set of shapes or a library of shapes? So what we're going to do is we're going to assume that you do have this library of shapes. You normalize them to have, first off, the same translation, rotation, and scale. So we want to rigidly align them because we only want to model variations in shape, not in rigid pose. And then we're going to do the same thing where we collect a huge number of SDF values and corresponding XYZ coordinates for each shape. It doesn't need to be the same XYZ coordinates. We just need to collect a set of these for each shape. And then what we're going to do is we're going to represent each shape by a randomly initialized embedding. So we're going to try to create an embedding space for this shape. So what this just means is it's just a randomly initialized vector. It can be size, in a deep SDF paper, it's size 128. We've gone as low as size 20. And then what you're going to do is you're going to train an MLP. But this MLP is like the last one, except it takes 2 sets of inputs. It takes both the coordinates, the x here, but also the vector embedding as a second input. And you're going to train that MLP to regress the SDF values for your whole library of shapes. Importantly, what ends up happening is you have a shared set of network weights for all of the shapes. But then you have this vector embedding, which although it's an input, it actually is trained or auto-decoded. So you train the vector embeddings while also training the shared set of network weights. And so the vector embeddings are specific to the shape in question. And once you do that, you basically essentially auto-decode an embedding space for your shapes. The nice thing here is that once your MLP is trained, you now can smoothly vary the SDF across both coordinates and also the shape embeddings. So what does that give us? Well, the first thing it gives us is, unlike point distribution models, there is no requirement for point correspondences. So this is really nice because now we've gotten around one of the major roadblocks with classic SSMs. We don't have this need. We don't need to make up landmarks anymore. So I have 3 exclamation points here because I'm really excited about that, because I think that is quite a powerful feature of these implicit shape models. Also, if we look at the embedding space, it seems to permit statistics that we can perform on it. So let's say, for example, we have 50 shapes. We have 50 embedding vectors. If we take the mean shape vector and then render that shape using our trained MLP, we get a meaningful shape, like on the top left, if we're looking at the MSD decathlon challenge for the liver. We can do PCA on the embedding space and look at what shapes come out. And the PCA variations seem to correspond to semantically meaningful variations. For example, the first mode corresponds to like a thickening or flattening of the liver. We can also interpolate between shapes. So we can interpolate between the embedding vectors, and then we get a smoothly varying shape that morphs from one liver to the other. And also the embedding space that we have seems to encode meaningful similarities. So on the right here, we have a TS&E embedding of the embedding space. And we can see that if embeddings are close together in space, it seems to correspond to similar shapes. And so this is really nice because it seems to indicate that what we've done is we've created a really compact representation of a very complex and nonlinear way that shapes vary, but we've compressed that down into a very compact embedding space. As I said, we've gone down as low as size 20 embedding space. Okay, the point of this slide is just to emphasize that although the concepts are somewhat straightforward, once you get your head around the idea of implicit shapes, there is a lot of important implementation details to get this working. Otherwise, it just doesn't work. I won't go into them here, but I encourage people who are interested to consult the paper on how that would be done. Okay, so that's how we gain an implicit statistical shape model. So once we have a shape model, we obviously want to do something with that. And in our case, we want to use that shape model to gain robust segmentation. So like classic point distribution models, we're going to represent our shape using a PCA basis. So we're going to take a PCA on the embedding space, and we're going to try to regress the PCA loadings to describe how that shape should vary given the current, how that shape should, the non-rigid pose of that shape given the current image. So that means that for any image, what we need to do is we need to determine its rigid pose and its non-rigid PCA loadings. So one kind of straightforward, obvious way that you could do that is we could just train a CNN encoder to directly output pose. So what I mean by that is we take the image on the left, a 3D image, put it in a 3D pose encoder, and it would regress our rigid poses and our non-rigid PCA loadings. Now, anyone who's familiar with medical imaging would probably wince at this idea because this is obviously a setup that is very prone to overfitting because we're trying to regress global parameters from a 3D volume. And it's medical imaging, so we don't have a huge amount of data. Also, these global parameters can be quite sensitive. So, small errors in the global parameters can create potentially large errors in the segmentation. And related to the overfitting, the search space here is really large because we might have like 9 rigid poses and however many PCA loadings. And we got to search the best combination of all these parameters. And so it's kind of a combinatorial problem that is very difficult to break down. So we don't do this. We never got anything like this to work. We honestly weren't that surprised for it not to work. And so we need something else other than this kind of direct regression approach. So the approach that we took is called an agent-based formulation. Now, if anyone's familiar with reinforcement learning, it has some similarities in the sense that we have an agent that's kind of exploring the environment it poses. But unlike reinforcement learning, we don't have to develop or come up with our own loss. We can compute the loss directly. So that major challenge with reinforcement learning is not something that we have to deal with. It's just we're using an agent. That's the only similarity. More specifically, we formulate our problem as a Markov decision process. So what that means is that we now inject the concept of state into the network. So the state is going to describe the current pose, the current rigid and non-rigid pose of the estimation process. And so given the current state, the network's then tasked with estimating a correction to that state. So it'll estimate a change to that state. And then the new state needs to be updated based on that change. And then based on the new current state, it'll regress another correction. Then the state gets updated, and then it'll finally have a third correction in this case. But we typically play out a longer episode than 3. And so this agent-based formulation, it's a Markov decision process because its decisions are only based off of the current state that it's sitting in, not the chain of states behind it. So if we have this agent-based formulation, it means that we have a concept of state. And so that means that the network needs to be aware of the state. So that essentially means that we need to inject observations into the network. We need to give observations to the network. So the way that we do that is we provide an extra channel to the encoder. So instead of just having an image, we also have, we render the mean shape SDF and we'll move it with predictions. So for example, if the network predicts translation 5 to the right, then we will move the mean shape SDF 5 to the right and for the next step. So, so the observations are encoded in this additional channel. And so the network learns that this channel is where it needs to seek information on what state it's currently in. So the agent-based formulation I just outlined is a general concept, but then there's a lot of important details. And the biggest challenge here is we have to come up with ways to really train this. And the reason this is challenging is because once you have an agent-based formulation, you kind of start quickly to deal with the issue of exploitation versus exploration. So you want your agent to learn like how to, quickly exploit the best paths, given the training data, but you also want to make sure it's exploring different states so that it knows what to do upon deployment, and it's not going to get confused. And so there's kind of two competing considerations here. So the way that we do this in training is that in training, we'll actually play out an episode of T steps for a batch. So for a batch, what we'll do is we'll start with initial pose. Then we'll randomly perturb the pose. And the reason why we randomly perturb this is, again, for this exploitation versus exploration balance. So that the perturbations here are really how we calibrate that balance. Then the network predicts the correction. And then there'll be, another random perturbation, and then it predicts the correction. So here we only have an episode of 2, but in reality, it'll be, an episode of maybe like 10 to 15, depending on what's happening. And so the nice thing here in this episodic training is it learns how to correct pose from a variety of situations, especially with these random perturbations. But then you play out the episode 2 times, so then it also learns how to exploit and how. So learns how to exploit and how to hopefully converge and stop when it's reached a good solution. In terms of the loss formulation, the major component that gets added is we have an extra loop here, this inner loop, which is the episode loop. And apart from that, it would be a fairly typical loss formulation. Okay, so this concept of episodic training is really critical to get things work, or the concept of agent-based formulation. But the episodic training is not enough. And the reason is because if you think about what's happening with episodic training is that you would play out an episode of T steps for one batch. So that means that network is seeing that same set of samples T times. And that's basically a no-no in deep learning, because that impairs that stochastic descent that we all know and love. And we ideally want to have kind of more variety of samples in there. And especially if you have a long episode, this can be a bigger problem. So so what we do is called something called inverse episodic training. And this is a fairly simple spin on episodic training. And the way this works is that we'll actually play out, given an epoch of samples, we'll actually play out the steps for all samples one by one. So what I mean by that is, let's say we have only 3 samples in our epoch. Obviously, we have many more in a practical situation. Is we'll play out the first step, which is random perturbation and the correction, for all the samples and save their states. And then we'll go back through the epoch again and do random perturbation and their model correction for the second step, and so on and so forth. We do that T times until we reach the end of our episode, and then we'd start all over again. So here, what this ensures is that we're always giving a variety of samples throughout the network training. Now, in terms of loss formulation, what this simply means is that the inner loop, the episode which was previously an inner loop, is now the outer loop. So that's the only kind of difference formulaically. Okay, so that was episodic. So we talked about the agent-based formulation, episodic training, inverse episodic training. All these things are critical, but it's still not enough to actually get the pose estimation working. And that's because they still haven't addressed one other major issue with pose estimation, and that is that we have a huge search space to explore, because we have the 9 rigid pose parameters and however many non-rigid PCA loadings that we're working with, and so this is something that we have to address. And this is actually this issue of having a huge search space is something that a lot of methods prior to deep learning, the classic statistical shape models, something they had to deal with all the time. And so the way that we deal with this is we're actually going to take an approach called marginal space learning, which was published back in 2008, and we're going to kind of adapt it and use it in a deep learning context. So again, this is another exciting part of our work, because it means it's another way that we're taking some of these concepts and approaches that had a lot of meaning and usefulness, and hopefully updating them a bit to make them useful for for deep learning, which is obviously very powerful machine learning architecture. So the way that marginal space learning works is that it's a technique used to break up the search space for pose estimation. So what you end up doing is, let's say you're trying to estimate your translation scale, rotation, and your non-rigid PCA loadings. So instead of trying to estimate it all at once, is you would train a pose encoder that searches for the optimal translation first. So only translation. Once that pose encoder is trained, you would then train a translation and scale encoder, whose starting point would be the endpoint of the translation encoder. And in this case, what it's doing is it's trying to estimate both scale and also fine tune the translation a little bit. So, and because you're starting from where the translation encoder ended, it means that your starting point should be quite good. So you only should need to do little fine scale adjustments to translation, but your search space for scale may be large. And then you do the same thing again for translation, scale, and rotation, where again, your search space for translation and scale are probably small, but rotation search space will be large. And then you finally do that with the PCA loadings. A key part of this, if we're talking about marginal space learning in this kind of deep learning training setting, is that the random augmentations that we perform are really key in also controlling that marginal space learning. So what that means is that when we're training the translation encoder, for example, we may have large perturbations, but when we're training translation and scale encoder, we're going to have smaller translation perturbations, but but large size scale perturbations. So basically, we kind of reduce the random perturbations for the prior step as we move to each step along the marginal space learning schedule. So despite this, so there is some complexity involved here, but this, without it, we weren't actually able to get anything to converge beyond translation. So these kind of concepts of breaking the search space down are indeed really important for getting this to work. Okay, so that was pose estimation. So the final thing to do, the final core component is local fine scale refinements. And here is where we actually use FCNs, because we're not anti-FCN. Actually, FCNs are incredibly powerful. But here, actually, what we're doing is we're using FCNs in a very constrained way, in a way that I think really sets the FCNs up for success. So we essentially use a deep level set based loss, where we only allow the FCN to predict kind of corrections within a narrow band of where the statistical shape model converged to. So the FCN has this really constrained and implicitly parameterized training and inference setup. And so, and the way that we do this also allows us to retain our surface formulation, so we don't lose our ability to regress a nice surface. So, so again, just the emphasis here is that we really do believe in FCNs, but we're just using it here as a way to kind of, as the FCNs to actually correct what should already hopefully be a robust estimation process. Okay, so that's the complete pipeline. So I think, as I hopefully made clear, the pose estimation process is the most complex part of this pipeline. It's probably the part that actually could require a lot more future work to simplify and make that process plug and play. But we're really happy with the end pipeline that we did have, because it did marry a lot of the deep learning approaches with kind of classic approaches together to produce something that I'll hopefully be able to convince you is quite robust. So as part of that convincing, let's just go over some of the results. So our main way that we validated this approach, at least in the publication, was via liver experiments, so more specifically pathological liver segmentation. So we trained basically our approach on the MSD liver data set, and we also tested on the MSD liver data set. But then we also have an external testing data set, which we did not train on. This is a clinical data set. And I would argue it's the most challenging liver segmentation data set to date, because it incorporates lesion types not seen in the MSD liver challenge. It's got treated lesions, it's got comorbidities that aren't seen. It's basically directly extracted from a clinic, from a hospital with minimal curation. So it kind of represents all the challenges that you would find in a real clinical data set. We tested our approach against the strongest competitors we could think of. So that, of course, includes NNUnet, HSUnet, which was a winner of the LITS challenge, which is the same data more as the MSD liver data set, although we retrained it. We also tested against an adversarial shape prior approach. So this approach means that we take the NNUnet that we know and love, and then we add a discriminator on top of it to discriminate the masks that it outputs, so to provide those implicit shape constraints. So this basically represents the best kind of anatomically constrained competitor that we could think of. So let's look at the results. So these are the intra-data set results. This means training on the MSD liver and testing on the same, not on the same data, but on the same data source. Unsurprisingly here, the best competitor, which is the orange, is NNUnet. And this just goes to show you how well engineered and made NNUnet is and still is. But even though the mean performance is the mean and median performance is roughly the same with ours, which is the brown here, our approach has much lower variance, much better worst case performance. And so it's essentially, even though we're using, we're training and testing the same data set, even in this situation, which is kind of very favorable to an FCN, we're still able to show robustness improvements. Even emphasizing that a little more is the Hausdorff distance for NNUnet is 29.1, where we go down to 21.4. So there is indeed added robustness even on an intra-data set experiment. But where I think our approach, shines even more is if we do the interdata set results. So here, interestingly, the best competitor is no longer NNUNet, it's actually adversarial learning. So again, this goes to show you that incorporating an anatomical constraint is really important for robustness. But even though the adversarial constraint, anatomical constraint did perform best of the competitors, our approach is still much more robust than anything else. Much better mean, median performance, much better worst case performance, much better best case performance, much smaller variation in performance. And even so, what we're really even excited about is that we have a DICE score that's almost 96%. And keep in mind that this was data, we trained our approach on the MSD data and just tested directly on this clinical data, which is highly challenging, has a lot of differences. And so we're very, very excited about these results. So I went over some of the numbers, but what do these numbers actually mean? Like, do they actually translate to kind of meaningful differences? And they do indeed. So here we have some qualitative results. And for example, we can see some of these FCN approaches, they make some of the mistakes I mentioned earlier, like, for example, leaking into the spleen. This patient, I believe, has splenomegaly, and so got confused. And this is not an error you would see in our approach. Again, here, like the FCNs missed this treated lesion. Obviously, this is not how a liver should look like. Any human familiar with liver would be able to recognize that. Our approach, again, doesn't have that issue. So even though it's never seen a lesion that's been treated before, it's able to produce a liver shape that that is good and robust. So indeed, it's not just numbers. These do produce meaningful differences in performance. And on the right panel, we're just showing some of qualitative differences. Basically, what this is just showing is that we can output directly a high quality surface that doesn't suffer some of these discretization effects. So it's maybe like it's an added bonus, let's say. We also did some auxiliary validation on larynx. I won't go into as much detail here, but larynx has got its own challenges different than the liver. Its main challenge is that if you want to segment the larynx, it's a very low contrast segmentation. So we tested against, again, very strong competitors, and we again show performance improvements, particularly in robustness. So I think this is a good point to end the talk. I probably talked enough. I'll just give some conclusions. I hope that I've given a convincing case that anatomical priors can ensure better robustness and performance upon clinical deployment. Our approach is the first to report a true deep learning based statistical shape model to the best of our knowledge. It outperforms the strongest liver segmentation FCNs we could find. And I would even go as far to say that there's drastic improvements in robustness there, especially when you deploy on in an interdata set manner. Our shape model is correspondence free, so it avoids some of those challenges with classic point distribution models, and it directly outputs a high quality surface. The work is not, 100% finished. I think the method's still highly complex, particularly with pose estimation. And I would really hope that, future work could focus on making that process a little simpler and more plug and play, because something that's, close to as easy and simple as how FCNs could be used would be, a huge boon. It'd be really, really nice. I'll just finalize by saying that at QBio, we're hiring intern and full-time employees. So if you are interested, please feel free to contact me, and I'd be happy to talk to you further. So I think with that, I'll end the talk, and I will stop my sharing. And I'd be happy to take any questions that people might have.
Thank you, Adam. So
actually, I guess I'll share again, just in case people have specific questions on slides.
Yes. So feel free to type your question in the Q&A session. So I have a question. So you mentioned the marginal learning strategy. I was wondering how much effect it gives.
We were unable to get it to converge without it. So, so if we just did inverse episodic training, we could get translation. If we only did translation, we could get that to converge, but we couldn't get translation and scale, let alone translation rotation and the PCA loading. So the marginal space learning was critical. It wouldn't work without it. And I would think that, maybe marginal space learning might not, I'm not saying that that's the only way to do it, but I think that some way to break up the search space is kind of critical to get this working. And that's something that is kind of not unique. I think that's a challenge. That's something that kind of the classic statistical shape models also had to do to get them to work, particularly in when we're talking about 3D segmentation.
Yeah, thank you. I was thinking whether techniques like self-supervised learning could have also get a similar effect to help as a pre-training.
Possibly. I think I would need to understand more by what you mean, but exactly by that, because I think self-supervised learning is like a fairly large topic. But yeah, there could be something there. Yeah, like if you have a specific idea, I definitely want to hear it.
Thank you. Yeah, I was thinking of maybe because it's kind of like using, I can't say pre-trained model because you train it with your own data. So I was thinking maybe using some pre-training technology, contrastive learning, all those ways can also get a good start point of converging. But yes,
possibly, yeah.
Yeah, thank you. We have more questions here. One question from the Q&A said, nice work. I was wondering what is the inference time for one case during testing?
Yeah, good question. It is, I think we timed it in the supplementary material, but I don't remember the numbers. But it's like less than a minute. It's probably about 15 to 30 seconds roughly, but I mean, don't quote me on that. I should have that numbers ready, but yeah, it's definitely longer than just an FCN, which just is, you just do one inference, because in this case you have to do you have to play out an episode, but you have to play an episode for translation, then translation and scale, translation, rotation and scale, and then finally with the PCA loadings. So there's several inference steps that are involved there.
Thank you. We have an attendee raised hand. So Jean Russell, I already permitted talking, so you can just unmute yourself and just talk about your question.
Okay, thanks so much. It's a very, very nice talk. Thanks so much. So I would just like to know first about the encoder. That it seems like you call it a CNN-based encoder estimation, right? It just encode the pose. CNN pose estimation.
Sorry, your mic, Jean, your mic is cutting in and out.
Oh, really?
Just a little bit.
Okay now?
Yeah, it's okay.
Okay now? Oh,
yeah,
it's okay now.
That's good. Yeah.
Okay, sorry about it. So I was just looking at your encoder that you said it's a CNN pose estimation encoder, right? So I was wondering whether it only encode the pose, but I thought it also encode the shape of the shape in the image, right? So I just want to make sure because when we see the output of the pose, the CNN pose, we have some parameters, mu plus w lambda. That's the z of the latent space. Does that only encode the pose, or it also has some shape informations? Yeah, it's here. Yeah, PCA loading.
Yeah. So Well, so the pose is the shape information. What I'm using pose to both mean the rigid pose and also non-rigid pose, meaning the shape deformations. So,
oh, yeah, okay.
Yeah.
Okay, just a terminology issue, because I was like, well, she does just only encode the pose, as we know. I mean, not local variation. How
No,
we
yeah, of
end
course
up
not.
having
Yeah,
the
of course
shape
not.
variation then. Okay, yeah,
Yeah.
that's very nice. And the second one is the last is MLP. Sorry, I don't really know about the MLP, but I would just, is it a neural network based framework?
Yes, exactly. So it's kind of like an old-fashioned term, multi-layer perceptron. But what it is it's just a fully connected. It's a network that only has fully connected layers. So in our case, I think it was seven layers. So basically 7 fully connected layers. It's like a you can almost think of it as a a one-dimensional network in our case.
Okay. Yeah, that's great. So if you go back a bit back on the architecture, where you have to use the Markov change, the Markov change method to be able to estimate the pose. Yeah, you explained that. I'm just trying to understand, but because the Markov change is in general very slow in estimating, I mean, because it has it's a sampling-based approach, and sometimes it's very slow. Couldn't you just use an encoder? I mean, it's like you have, if you go back in the architecture where you have the CNN pose estimation encoder, but yeah, here, can we just have, like you have the image here without having any Markov chain inside this, you use a CNN-based encoder to have some code as an output where you have maybe some part of some variables of the vectors of the output from this encoder, where you have some variables would explain the pose and the other one would explain the shape variation without using any Markov change before. I mean, just asking, just want to understand.
Yeah. Obviously, that would be really nice if we could do it, but we never got something like that to work because you're basically asking it to regress global parameters. So medical imaging, we don't have a ton of data, so we're already have an uphill battle with overfitting because we're trying to regress global parameters from a 3D volume. And it's also it can be quite sensitive. So basically, we did try it because we had the same idea, but it just never worked. And the other challenge there is that you are asking it to regress global parameters, and these can be quite sensitive. So small errors in the global parameters can produce very large errors in the segmentation. And so there's not a lot of opportunity for the network to, it basically has one chance and doesn't have an opportunity to try to correct itself.
Yeah, I completely understand that so much, and because I also tried something like that, so I was really overfitting. So I'm happy that at least you tried also, and then I'm more comfortable now. That's it's just my problem because it doesn't really work that way. Like as we explained. That's very, very nice. I wish maybe we can talk more. Maybe I will let other people ask questions, but I'll maybe contact you and then we can talk more because it's very interesting for me.
Yeah, please feel free to email me. I'd be very happy to correspond with you.
Yeah, that's great.
Thank you. Thank you. Do we have more questions here? Yeah, feel free to either type in chat, type in Q&A, or just raise your hands.
I can.
Yeah, sure, John. You can ask questions if you got more questions.
Not others. Sorry. I don't want to kidnap the talk. Sorry. So I was just also asking, what do you use PyTorch for coding or just a curious question? So, but
yeah, PyTorch.
PyTorch. It's not yet open source, as you said. If you understand correctly.
This work?
I mean, the code is not yet released, right?
It is. It's released. It's in a We released it publicly. It's in a state that it's there's some it got released and then by our intern, but didn't get cleaned up by the time I left Pi. So so be forewarned on the state of the code, but it's released. You could find the link in the paper.
Oh, I can find the link because I was looking for the link. I couldn't find the link.
You send me an email and I'll send you the link.
Okay, that's cool. And maybe you can. How can I get your email? Sorry.
So can you find the paper? And my email should be on the paper.
Oh yeah. Thank you so much.
No problem.
Yes, thank you. Yes, thank you, Adam. This is a wonderful talk, and the method very elegantly combines the traditional methods and deep learning. Very wonderful talk. We are about the time. So if we get approval, we will post the video on the YouTube channel.
Okay, great. Yeah, looking forward to that. And thank you everyone for attending the talk, and I appreciate this opportunity, San.
Yeah, thank you. Thank you for joining the talk. Have a nice day.
Bye now.